So uh, continue our this detour into how we had the rule of measurements and in for an observer and how we could account measurements in the quantum mechanical sense. So now we have to just because the role of probabilities was very much there, the frequentistic interpretation of probability, which had some problems, and it was circumvented or obviated by taking recourse that to that the tautological nature of these statements, logical statements. They don't describe the logic of the physical world. They are more in coherence to the logic of those statements rather than logic of the measured physical world. This is one way of doing with this. The other way of doing with the same thing is by saying that 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 the equality is not there. So if we have there is an inequality, we have to invoke an inequality where we just assume the equality of statements regarding those different observables. So these were two way of doing away with this thing. So here we will see what are the nature of these probabilities. These uh, probabilities or events or mathematical probability nature of probabilities and statistical assemblies in quantum mechanics. So because we are taking these probabilities, they might correspond to different events or probabilities. So in the first case, for example, even the word very interference of probabilities, because we are going to use calculus, rather probability calculus. Sometimes the what I should say resemblance or semblance of statements of probability calculus vis-a-vis the statements of probability amplitudes makes the picture somewhat confusing. So it's probability means we in quantum mechanics we talk of probability uh, amplitudes rather than what I should say probabilities. So in the mathematical sense, probabilities don't interfere, but in the physical sense, two probability amplitudes we have a superposition of that amplitude is there. And when we talk of, for example, more probable statement, of more probable probabilities. So it we see vague statement because probability is indicative of that its result is to be enumerated. So there needs to be some hunch, some guess, some assumptions which are going to just have predictions for the desired outcome. Even though if we are going to repeat the experimentation in a given sample in a given time, the time should not be infinite in that sense. So once we take these probability statements of probability, which are mathematical statements or which are assumed from particular interpretations of probabilities, mostly frequentistic interpretation of probabilities, and we are going to adjust or couple or make them semblance to the probability amplitudes or probability states which correspond to those states which are evolving in space and time. So there is a lot of extrapolation or interpolation from the mathematical way of defining probabilities and the probabilities we are basically accounting them in some physical sense. So one important thing which is there is that, for example, we say in most cases, what we say, the determination of these initial probabilities. So how should we define the initial conditions, whether in quantum mechanics or in general? So it's not a mathematical problem, not a mathematical problem, but a problem of physical problem. So what were the initial conditions from which the subsequent events can be formed or formulated, or you can say is that how by the induction of by induction or by enumeration or posterior determination of probabilities. So induction by enumeration can also include stats. You can also say it's a statistical inference. So we just have, for example, statistical induction by enumeration or posterior determination of probabilities. We just go to the starting thing. And we have statistically inferred probabilities. So in the sense that probability amplitudes, the way we talked of, they belong to physics. They do not belong to the calculus of the statements about the calculus of the probabilities. So in the same way, so our interpolation to induction by enumeration or posterior determination. So we have a prospective thing. So we are going to in probabilities, we are going to predict something in some impending future, but the assumptions are dependent upon the initial conditions. And the initial conditions cannot be extracted from mathematical assumptions. There is more to it, so which we have to take into consideration while we are just taking entire these things. And words like potentialities and potential probabilities doesn't make sense because it is we are making a statement for an impending future, a prediction about an impending future, and the initial conditions have to be properly seen, how we define them via and then we can just have these statistical inferences and other things. Now, now the question is like, the eigens, once we also said about eigenfunctions, eigenstates, and they may be continuous, they may be discrete, and we also talked of something called practical eigenstate functions or states. So the question is so there come in literature something called pure and mixed. So in the scheme of the eigenvalues and eigenfunctions, what are the eigenstates, what are the eigenfunctions which the given eigenvalue to eigenfunctions which will correspond to given eigenstates, and they will correspond to given eigenvalues. So in the case of continuous and discrete cases, so there can be class of eigenfunctions which will correspond to the range of eigenvalues, which may be discrete or which may be continuous. And there are delta V of how we can classify them. Then there's a further another thing is that even in those discrete or continuous class of eigenfunctions which will have range of eigenvalues, where can we differentiate one from the other in the sense that if we have a reference class or psi states, so there should be a way. So for a similar class, similarity class, or if I use the words of renormalization, that class states that the similar eigenstates which will belong to certain probability, those probabilities which may be discrete or continuous, which might have some mapping to some unique eigenvalues, they may be belong to a certain particular class. And that class can further be classified in terms of pure states as well as mixed states in that sense. So if you can make a repetitive measurement on a certain class of eigenstates, if they will lie in certain class which cannot be differentiated, so you can say they belong to pure states. And even if after measurement you cannot arrive at by systematic procedure the same state, we can characterize them as mixed states. So the measurement comes as a thing. How a measurement will lead one class into pure and other class into mixed. So that's also a question. So if there is a psi function of mixtures, it can be expanded as an eigenfunction. So we can come to how we represent them. So if there is a psi function, psi of q, we can have a measurement like this by k, q. So sigma k square is the probability measurement of values uk. Since this is ultimately found in those cases in which individual system is represented by eigenfunctions, so probability of S. So we are coming to our previous thing now. So if we represent it like this, so let us consider a question not measured by this. So we are coming to our previous thing. So measurement of, so if we define the certain class of measurements which have a particular frequentistic interpretation of probabilities, so we came to the question that probability, sum of probabilities is not equal to the sum of probability is not equal to the total probability, square of the probabilities. So if you define it like this, and another state psi q is defined as rho m zeta m q, and we have a probability of this probability is defined as probability of this is S, so you can have this S M is rho m square is sigma k. So we are coming back to our previous thing. So where we define two class of measurements, in which we sometimes ignored one of them, and in this state we define two states, phi and psi. Phi in terms of psi in terms of this, and phi in terms of this, such that Km is equal to zeta m q. So here psi it's mediated by this, here it's mediated by this. So you can have probability of S of mu can be ck km square is equal to k sigma k square or km square. So again, this probability of sum of squares is not equal to probability total probability square. So this is a contradiction which was presented previously. This contradiction can also be just as a statement of the previous contradiction of this thing, where we said that a probability of this cannot be ui mv mw wm is not equivalent to probability of mu ui mw. So it follows it's not permissible to consider. So the contradiction can be, these two contradictions can be, so if this is not holding this thing, so it can be said in a statement that formally if a measurement is not merely a repetition of preceding measurement means the assemblage created is by it is irrespective of its result is a mixture. So you can say, so you can the previous classification of pure states and the mixed states. So if the measurement is not merely repetition of the preceding measurements, so the repetitivity is not there. The assemblage created by its irrespective of its results in the it is irrespective of its results in the mixture. So that the purity part is gone. So if it's mixed, so we can reaffirm it that measurement has induced some changes in the observables. So you can say, mathematically speaking, the question arises whether the term physical situation is wider than the term pure case. So it's very important. So the question, the term physical situation, is so the question is whether the term physical situation is wider than pure case. Of course, it can be, it's wider in that sense. Physical situation is wider in the pure than the pure case. Yes, yes. This would be so. So you can say the more other way of saying the same thing is like this: is that pure case represents, it's basically pure and mixed in the sense that how we are going to have those measurements on different states, which will have eigenvalues in those broad class. In the process of measurement, if we are able to differentiate one class of states, or in the university, one universality class from the another universality class. So so if we are not able to differentiate, then it's a pure state. If by the act of measurement we are able to differentiate, then we can have mixed states. So this means measurement has changed those classes into something different. So if you say, in that sense, pure case represents the utmost degree of homogeneity attainable in quantum physics. Yes, yes, that's it. So now, if we want to see that present, if you want to summarize what we have enumerated as basic principles of quantum mechanics, we can say that number one. So, our basic principles of principles of basic principles of quantum mechanics. Number one. So basic, the physical entities, basic physical entities in a given context are represented by operators, eigenfunctions, eigenvalues, and they are determined by Schrodinger equation. So in that crisp sense, the physical entities, their representation can be formed in these things, but then they can be represented in Schrodinger equations. And or first Schrodinger. So in the book we have first and second Schrodinger equation. You can have time dependent, time independent Schrodinger equation. So you can say in that sense. And the second is that the wave function psi, there are some rules. Rules are like Rule is one rule of eigenvalues. One rule is that eigenvalues constitute possible values in a given context. Possible values in a given context. The context may be whether they are orthonormal or orthogonal states, which might correspond to given eigenvalues. In degenerate cases, there may be more than one eigenstates which might have unique eigenvalues. And the other, in this rule one, we can have sub-rule that rule of spectral decomposition. We can have a function expand psi into eigenfunctions of considered entity. The square of expansion of sigma or sigma u then determine probability of the. So we can have both discrete and continuous spectrum of eigenvalues, which might have their own, what I should say, probabilities, which can be constructed while we are going to see whether eigenvalues can be taken from discrete states, spaces, or in that continuous spectrum. To be more precise. This is second rule, and the third rule can be so you can have the law of time dependence. So we can have an explicit, how we have on this Schrödinger's time independent equation. So we can have explicit dependence of psi. Which is given by, in this book, we have second Schrödinger equation. So which is also called, on this time independent Schrödinger equation, other is time dependent Schrödinger equation. And if you remember, we had seen the explicit construction and implicit construction of psi in terms of t, and that exercise is there. And the fourth one is that we should have a quantum mechanical definition of measurement. So one is the classical definition of measurement, that in a given ensemble of states, the observer or the measurement doesn't in any sense change the measured. But in the quantum mechanical sense of measurement, it's, in the previous class we have seen how, and there is a mathematical way of also stating the thing. And it comes more in the case of two non-commuting operators which are operating on given states. Their commutator may not be necessarily zero. So which means we cannot have simultaneous measurement of two non-commuting operators exactly. So that has both mathematical as well as physical implications. And from these four postulates, you can have the principle of interdeterminacy and disturbance of object by measurement. So you can say that in this book, so the interdeterminacy principle of interdeterminacy or disturbance of object of measurements are not, so they don't come as basic principles. We can arrive at them, and they can be taken as both derivable principles if we construct these four. So whether whether it's a principle of interdeterminacy or whether it's a principle of disturbance, we can have consider them as derivable principles. They are not ab initio. We cannot necessarily take them. So in the last lecture also, we at the end arrived from a contrived reasoning in Reichenbach that disturbance as a part and parcel of measurement, that quantum mechanical measurement induces disturbance, and that's part of that postulate. So here we can also arrive the same from indirect argumentation. So we'll stop.